Welcome, my name is Philippe Verzeep and this webcast accompanies my book Data Analysis. In it, I will show you how to test for and if necessary correct serial correlation. If we run a regression, we always want to find out if the coefficients we have are in fact significant. The reliability of our coefficients is given by the standard errors. However, these standard errors may be affected by certain methodological problems, including serial correlation. Serial correlation, or otherwise called autocorrelation, is a situation where one residual is related to the next residual, therefore spreading information between various observations, and meaning that if we have a big spike, it will linger on in our residuals for quite some time. These effects will influence the standard errors, which are calculated without any consideration of changing reliability. So we might get biased standard errors and therefore biased t-statistics and probabilities p-values, which are not what we need to be, them to be either. To detect this problem in regression, we first estimate the regression and then go to view residual diagnostics, serial correlation, LM test. This is the Royce-Godfrey test as described in the book. Now, the next question we have to answer is how many lags we want to include. This is how many periods we go back. The choice can be somewhat complicated. If you choose a lag number which is low, you might miss serial correlation, which may only exist in higher lags. On the other hand, if you include quite a bit of lags, a too high a number, you will likely drown out any serial correlation, because there will be a lot of white noise in the auxiliary regression. So it's important to find a correct number, and it's often a good idea to try several setups. Let's start with the standard of 2. We'll see that an auxiliary regression is estimated with the residuals as dependent variable. Independent variables are the original regresses x variables in our equation, but also the residual 1 period back and the residual 2 periods back. Those are the interesting ones. We run two tests on these. We run an f-test on the joint significancy of these two coefficients for the residual 1 period back and 2 periods back. And also we test the R-squared of this auxiliary regression. This auxiliary regression should have an R-squared of 0. There should be no pattern in the residuals. Now, in this case it's quite close to 0, however the test statistic is in fact the observations multiplied by the R-squared. And this, as well as the F statistic, gives us p-values which are below 5%. This means we reject the null hypothesis, we reject the idea that there is no serial correlation. In other words, we have serial correlation, we have a problem. Now, if we want to correct for this problem, which is by the way related to the first order, this is the one that's significant, we need to weigh the various observations. We can do this by a so-called GLS transformation, generalized least squares. The practical implementation of this in e-views is the so-called Newey-West algorithm. We can access this by clicking on Estimate, going to Options, and in the drop-down list for coefficient covariance matrix, we select HAC Newey-West. This will apply the Newey-West algorithm and we'll get new estimates for our standard errors, which are now corrected for serial correlation. In this case, we'll see that the conclusions don't differ that dramatically, although this could very well have been the case. We only know this once we have corrected. By the way, you can identify a corrected equation with this line, HAC standard errors and covariance. The rest are settings that you may want to adjust if you're an advanced user, but the default will serve most purposes very nicely. So in sum, the coefficients don't change, but the standard errors do. And that means you will have a correction for serial correlation, and these results, in the absence of other problems, would be